I want to describe a specific feeling that I think a lot of Mac users running local AI have experienced, and I want you to tell me the comments if this sounds familiar. You set up a local model, you wire it into a coding agent. The first few turns feel incredible, and you think, this is it. I've finally got a real local AI coding assistant running on my own machine. No API costs, no privacy concerns, no latency from a remote server. And then, somewhere around turn 12, it starts to change. The first tool call that turn takes 20 seconds, then 30. By turn 20, you're waiting 90 seconds for a response. Nothing about your task changed. The model didn't get worse, the questions didn't get harder, the context just got longer, and something under the hood is quietly recomputing the entire conversation from scratch every single time. I spent a long time thinking this was a hardware problem. More RAM, bigger model, better quantization. I tried all of those things, and to be honest, they helped a little, but they didn't fix the actual problem. The actual problem is a caching problem. And a small open source project called oMLX, with over 18,600 stars, built by one developer named Jun Kim, is specifically designed to fix it. This video is about what it actually does, how to set it up, how to wire it into Claude Code, Cursor, and other agents, and whether it holds up on turn 40 of a real session rather than just a demo. Let's first understand why local agents slow down. Apple Silicon is, on paper, one of the best local inference platforms available right now. Unified memory means the CPU and GPU share one pool. A quantized model can live in RAM without shuffling data across a bus the way a discrete GPU setup does. Apple's own MLX framework was built specifically for this kind of workload. The memory bandwidth on a Mac Studio is good. If you just want to run a model and chat with it, a Mac is excellent. The trouble starts when you stop chatting and start agenting. A coding agent doesn't just send one message and wait for one reply. It rereads most of your prior context on nearly every turn, calls tools, gets results appended back into the prompt, and repeats that loop dozens of times. Turn after turn, the prompt is almost identical to the previous turn, except there's one new tool result at the end. That near-identical prefix is the key detail. Most local inference servers, including the standard MLX server, treat a near-identical prefix as a complete mismatch. They discard the entire KV cache and recompute from position 0. On a short prompt of a few hundred tokens, this is invisible. On a 20,000 token session that's accumulated 15 tool calls, this is the difference between a 2-second reply and a 90-second one. The project's creator described this exact pattern as oMLX's motivation in a post on Apple's MLX GitHub discussion board. Coding agents send requests with shifting prefixes. The prefix keeps almost matching the previous turn, but the match isn't perfect because of the new tool result appended at the end. Every existing MLX server was treating those near matches as full mismatches and recomputing everything. That specific bug is what oMLX was built to fix. Understanding that the problem is a caching problem, not a hardware problem, is the whole reframe. And once you see it that way, the solution oMLX proposes makes immediate sense. Now let's on. The core of oMLX's solution is a 2-tier cache that survives prefix, drift, and even server restarts. Here's how it works. A standard inference server keeps the conversation's KV cache, the computed representation of everything the model has already read, in GPU memory. When the prefix shifts slightly between turns, that cache gets invalidated. Everything that was computed gets thrown away, and the next turn starts from scratch. oMLX replaces that with 2 tiers. Frequently used cache blocks stay in a hot in-memory tier. When that fills up, blocks are written to a cold SSD tier in a format called safe tensors, using block-based management with prefix sharing and copy on write. When a later prompt matches a prefix that was evicted to disk, those blocks get read back from the SSD instead of being recomputed from scratch. Think of it like a librarian who never reshelves a book you checked out recently. Ask again later, even after the library closes and reopens, and it's already on the counter. Now, SSD is not RAM. Reading cache blocks back from disk takes real time, just far less time than recomputing every token. And this is where I want to be careful about what oMLX actually does and doesn't improve, because the distinction matters before you decide whether to set this up. The cache reuse attacks one specific number: time to first token, how long before anything streams back. On long agentic sessions with repeated prefixes, this number drops dramatically. But it does nothing for the second number: generation speed, how fast tokens arrive once the model starts streaming. A slow generating model stays slow. It just starts sooner. The 90-second wait at turn 12 was almost entirely time to first token, not generation speed, so oMLX attacks exactly the right thing for exactly this use case. But if your model is slow on a short, fresh prompt, oMLX won't change that. Different problem, different fix. With that framing in place, here's how to actually get it running. oMLX requires macOS 15 Sequoia or later, Python 3.11 through 3.13, and an M1 through M4 chip. Before you install anything, update macOS if you haven't. I learned this the annoying way when an older macOS version gave me errors that had nothing to do with oMLX and took me an hour to trace back to the OS. There are 3 install paths. For most people, the first one is right. The macOS app path is the cleanest. Download the signed, notarized DMG from GitHub releases, drag it to applications, launch it. A welcome screen walks you through setting your model directory, starting the server, and downloading your first model. The app also installs a lightweight CLI shim so you can control it from the terminal too. I used this path, and it was 5 minutes from download to first response. The homebrew path is 3 commands, which I will give you in description below, and I will also add commands for people who want to build the optional MCP support or customize anything. One thing to flag before you pick your path. If you plan to serve any of the models that have native custom kernels like GLM 5.2, Minimax M3, or Qwen 3.5, a plain pip install silently skips those kernels and the model falls back to a much slower code path. The project reports the fused prefill kernel running roughly 30 times faster on an M3 Ultra for those models. Getting the kernels requires full Xcode, not just command line tools. This is the simplest reason to prefer the DMG for most people. It comes with everything pre-built. Once you've installed, confirm it's alive with a quick curl. Now, after doing all this, oMLX auto-detects models from a directory you pointed at. LLMs, vision language models, embedding models, and re-rankers all get picked up automatically. And here's the detail that saved me a redundant download. It reads your existing Hugging Face cache and LM Studio folder directly. If you've already downloaded models for other tools, oMLX can serve them without you downloading anything again. Yo can access admin dashboard by just adding /admin in top URL, and it has a built-in Hugging Face model browser where you can search and download directly from the interface. Useful, you don't need to leave the tool to find models. The sizing advice I'd give you is the same advice I wish I'd received earlier. Size the model to your RAM, not the biggest file you can find. Leave macOS 4 to 5 gigabytes of headroom. It needs that for itself, and it'll take it whether you plan for it or not. Then budget the rest for weights plus KV cache growth. KV cache grows as your session gets longer, so on a 16 gigabyte machine with a 9 billion parameter model at 4-bit, you have room for a real session. On a 64 gigabyte machine, 30 to 40 billion parameter coding models work well. On Mac Studio class hardware north of 400 gigabytes, oMLX's benchmarks target the largest models. This is the section I spent the most time working through because the connection method differs by tool in ways that aren't obvious until you're already halfway through the setup. Claude Code has one quirk. It takes its server address from an environment variable at launch rather than reading a config file. oMLX serves a native Anthropic compatible endpoint at v1/messages, so no translation proxy is needed. You just set 3 environment variables before launching Claude. oMLX also ships a Claude Code specific feature on top of this. Context scaling, which reports token counts so auto-compact triggers correctly for a smaller local context window, plus SSE keep alive to prevent read timeouts during long prefill. That's not a generic compatibility checkbox. It's a detail that someone thought about specifically for agentic sessions, and it shows. Cursor is different. Its local model setting lives inside the GUI, not a file on disk. Open Settings, go to Models, find the OpenAI API section, flip on Override Base URL. The exact label has been renamed before, so it may look slightly different in your version, and put anything non-empty in the API key field since oMLX on localhost doesn't check it. Add your loaded model under Custom Models using its exact name from oMLX. One thing to remember, disable Cursor's default models so it doesn't also try to validate against OpenAI's servers. That validation will fail because you're not pointing at OpenAI. OpenCode, Codex, and PyAgent all support one-click configuration through oMLX's own CLI launcher. One command updates the tool's config and starts the agent. The existing config gets backed up with a timestamped .back file first, so if something looks wrong, you can restore it. One honest flag on the Copilot integration listed in oMLX's README. GitHub's actual Copilot chat authenticates through OAuth against GitHub's own servers and isn't built to accept an arbitrary local base URL. The Copilot integration in oMLX's dashboard either targets a different tool with a similar name or works through a mechanism I haven't been able to confirm from public documentation. Check the admin dashboard's integrations tab directly before assuming that one does what the name implies. Here's where I want to give you real numbers rather than impressions, and be honest about where each number comes from. oMLX's own published benchmarks, first party, clearly labeled, run on an M3 Ultra with 512 gigabytes, show generation speeds around 45 to 59 tokens per second for an 8-bit Qwen 3 Coder Next model across contexts from 1K to 32K tokens. Continuous batching reaches roughly a 4.14 times generation speedup at 8-way concurrency versus a single request. Treat those as upper bounds on high-end hardware. A 16GB MacBook Air will see lower numbers. The independent data point I found most interesting came from a developer's published write-up comparing oMLX against raw MLX. He went from about 20 seconds to process an 8,700 token context on standard MLX to a warm cache response fast enough that he reran the benchmark to double-check it. That's a third-party account, not a controlled test, worth reproducing on your own machine before trusting it fully. The honest summary of when it helps? Cold start time to first token isn't meaningfully different from raw MLX, because there's nothing cached yet on the first turn. The entire benefit concentrates in warm, repeated prefix turns, which, in a coding agent session, is most of what you're doing. Turn 1 is cold. Turn 12 is warm. Turn 40 is where the difference is most dramatic. To confirm it's actually working during a real session, watch the admin dashboard. The hot and cold cache panels should accumulate blocks rather than reset every turn. If you see a full reset every turn, the most common cause is system prompt or tool schema content being reordered between calls. The cache uses prefix matching, and a reordered prefix looks like a different prefix even if the content is identical. I want to be direct about who this is for and who it isn't. If you're using a local model, mostly for one-off chat, you type a question, it answers, you move on, oMLX's caching won't change your experience meaningfully. The benefit is almost entirely concentrated in agentic sessions with long, repeated prefixes. That's the exact pattern of a coding agent running for 30 or 40 turns on a real task. If that's not your use case, the tool is real, but the gains you'll see are modest. If that is your use case, and it's mine, oMLX is the most targeted fix I've found for the specific failure mode where local agents feel fast at the start and crawl by the middle. It doesn't make your model smarter, it doesn't increase your generation speed, and it doesn't change what model you can run on your hardware. What it does is make turn 40 feel like turn 1, which is the thing that was making long agentic sessions feel broken on a machine that should be more than capable enough. 18,600 stars in a project that launched to solve one very specific problem, built by one developer, Apache 2.0, and already connecting to Claude Code, Cursor, Codex, OpenCode, and Pi out of the box. That's the kind of project I wish more people were talking about before they spend an afternoon troubleshooting a slow agent and concluding they need more RAM. The links to the repo, the installation guide, and the integration instructions are all in the description. Hit the like button if this pointed you at something you hadn't seen before. Subscribe for more practical local AI breakdowns. And drop a comment with what you're running on your Mac and what you're using as your agent. I'm curious whether people are finding oMLX fixes the specific problem they're hitting, or whether there's a different failure mode I should be covering next. See you in the next one.